Hello everyone and welcome to the lecture on electric fields for Physics 1512, General Physics 2. Depending on what course you took General Physics 1 or what section you took General Physics 1 in, you may or may not have run into the concept of field before. So I'm just going to work from the assumption that the concept of field is brand new. And in some ways, field to me has always seemed like a concept that was made up by physicists, but it's a useful one. And it helps us solve problems more efficiently down the road, even though when we first talk about it, it can be difficult to see the reason for doing so. So I'd actually start off by a question of a more simple question, perhaps. What is a field? Well, when you think about the place where you hear field used in your life, okay, we have a hay field, that's where we grow hay, or a cornfield where we grow corn. Or there's a baseball field where we play baseball, a football field where we play football, etc. So fields that we are familiar with are areas where a certain event takes place. And in some ways, that's a useful framework to think about fields in physics. Fields are areas, and they're areas around certain kinds of objects where certain kinds of effects take place. Given that we're talking about electric fields, we're talking about the regions around objects that have a net electrical charge, and they are places where other objects that have electrical charge can feel a force, and we frame it by saying that force comes from the field. So let me try to walk through this with comparing and contrasting gravity and electricity. So you learned about gravity in General Physics 1, and so we think of objects being gravitationally attracted to Earth through that force that Earth puts on them. But there's another way you could frame this thinking. You could say, here's Earth. The area around Earth is where gravity from the Earth has its effect. So I'm going to call that region around the Earth the gravitational field. And then when you put a mass into that gravitational field, it feels a force from the gravitational field. In fact, you probably didn't frame it this way, but that 9.8 number you learned in General Physics 1, well, you can write that as 9.8 newtons per kilogram, and that can be used as the strength of Earth's gravitational field near the surface of the Earth. I don't have to do a complicated calculation involving the mass of the Earth every time I want to know how much gravitational force is put on something. Instead, I can just take the mass of that object, 1 kilogram, and multiply it by 9.8 newtons per kilogram. That's the strength of Earth's gravitational field, and that tells me how much force that mass feels at that location in Earth's gravitational field. Well, similarly, if I have an object that has a net electrical charge, the region around that object is where the electric field exists. And the electric field is a region where an object that is another charge will feel a force. It gets a little more complicated than gravitational fields because gravitationally masses always attract to each other. Here, it depends on what charge we have on that other object. So if on that little blue object I put in there, it is a positive charge. It will be pushed away from the larger charged object. If the small charge is negative, it will be attracted towards. So depending on the sign of the charge, you get different behavior in an electric field. So we define an electric field as the force that is exerted on a small test charge divided by the charge on that test charge itself. If you are unfamiliar with the notation here, I'm using the 3 parallel lines to be defined as. So it means equals, but it also means this is the definition of the thing. Electric field, like force, is a vector quantity. So when we're dealing with electric fields, we have to worry about the direction things are in. Opposite charges experience opposite forces in identical fields, something we alluded to on the previous slide there. If I have an electric field in this room and I put a positive charge in it, it'll go one way, but I put a negative charge in, it'll go the opposite way. So you can see this if you do a little bit of algebra on that definition of electric field. If you take the electric field as being the force on Q divided by Q and solve that for the force on Q, you'll see that the force, vector quantity, is equal to the charge times the electric field. So if the electric field is in a set direction, depending on whether you multiply it by a positive or a negative charge, you'll get a positive or negative force, which indicates the opposite direction of those forces. The principle of superposition still applies. So here early on, when we're first learning about electric fields, we're actually going to calculate the electric fields from a series of point charges. Now, in truth, electric field doesn't really buy you any advantage if you're only working with a series of point charges. But we do it because it's the easiest framework to learn about the concepts of an electric field. Where an electric field is really advantageous is if I have many, 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 many charges. So at the end of this unit, we're going to see a device called a capacitor, which has a whole bunch of charge spread out on a surface, in fact, two surfaces. And if I had to calculate how much force each of those individual charges had on anything that I put in that system, it would be a very long calculation. If instead, though, I can characterize the electric field that exists between those two plates, it becomes a much easier thing to consider. And finally, you can use Coulomb's law to find the electric field due to a point charge. So if you take that definition at the top of the page and you say, well, this force on this test charge is described by Coulomb's law as the Coulomb constant times the charge that is creating the electric field times the test charge divided by the distance squared. Divide that all by the test charge. The test charge term cancels out, and I'm left with just kq over r squared, which is the relationship that we use to calculate the electric field from a point charge. So let's actually do this and get a little bit of practice. There's a couple of practice problems here at the end of this lecture. If you have an object that has a charge of negative 3.6 microcoulombs and a mass of 0.012 kilograms, if it experiences an electric force due to a uniform electric field that is in equal magnitude to its weight, what is the direction and what is the magnitude of that electric field? And if the electric charge got doubled, but its mass stayed the same, what's going to happen to it? What is the magnitude and direction of the resulting acceleration? So to start, here's my object. It has this charge on it and it has a mass. So if it has a mass, it's going to have a downward gravitational force from the Earth. And because I'm told that it's balanced here in this electric field, there must be an upward force on this object from the electric field. I draw that vector actually the same size as I draw the downward vector because this is balanced, which means the magnitude of those forces must be equal. So from that, I can apply Newton's second law, net force equals mass times acceleration, and say, hey, the force on this object from the electric field minus the force on the object from the Earth has to equal 0. Or you could write it as the force on the object from the electric field is equal to the force on this object from the Earth. Well, the force on the object from the electric field is equal to the charge Q times the strength of the electric field. The gravitational force is equal to m times g. G is often called the acceleration due to gravity, but could just as well be called the strength of Earth's gravitational field. And if you solve that relationship for E, you get mg over q, and then it's a matter of plugging things in to get a numerical value for the strength of this electric field. So the mass is 0.012 kilograms. Earth's gravitational field is 9.8 newtons per kilogram. The size of the charge we were given is 3.6 microcoulombs, so that's 3.6 times 10 to the negative 6 coulombs. Notice I'm just plugging in a magnitude here. I'm not worrying about the negative charge because I'm going to worry about the direction piece independently of this calculation. And if you punch all that into your calculators, you get about 3.3 times 10 to the 4th newtons per coulomb. And electric fields are measured in units of force per units of charge, most commonly newtons per coulomb. The electric field, however, is in the downward direction, and here's why. If this is in fact a negative charge, then the direction of the force that it feels, which is up, is opposite to the direction of the electric field. Freely moving negatively charged objects actually move against the direction of the electric field, and that means the electric field here, just like the gravitational field, is in the downward direction. All right, second part of the question. What happens if we double the charge on the object and the mass remains the same? What's the magnitude and direction of the acceleration? Well, I'm going to go through the formal calculation here, but there's a quick way to get this answer too that I'll mention at the end. So here I would say, okay, well now twice this force on the object from the electric field minus the force on the object from the Earth equals mass times acceleration. I've made this force from the electric field twice as big. QE equals MA because the force from the electric field was QE, right? But now it's 2QE. And we know from part A that QE is equal to m times g. So that means if I cancel one QE and mg, I'm left with simply one of the QEs equal to mass times acceleration. If I go ahead and solve that for acceleration, that's Q times E over the mass. So you take the charge, 3.6 times 10 to the negative 6 coulombs. You take the strength of the electric field, 3.3 times 10 to the 4th Newton per coulomb. And if you multiply those together and divide by the mass of 0.012 kilograms, you find, surprise, 9.8 meters per second squared. Actually, that shouldn't be a surprise, because if the electric field used to be the same size as the electric force used to be the same size as the gravitational force. Now you've doubled the electric force, but that means the net force is equal in size to what the gravitational force on this object is, which means the acceleration is going to be the same as if I let it accelerate under the influence of gravity alone, which we know from our work in General Physics 1 as being 9.8 meters per second squared. So the acceleration here is 9.8 meters per second squared, but that electric field is pushing this charge up, so the direction of the acceleration would be in the upward direction. I'm going to wrap up by one more sample problem where we look at this concept of superposition. In other words, working out individual pieces of the solution, then adding them all together to get the end result. And this one at first blush looks like a lot of work, but we're going to cut that down considerably with our analysis here. So the drawing shows two situations in which charges are placed on the x and y axes. They are all located at the same distance from the origin. Without doing any formal calculations, does the electric field at the origin in part A have a magnitude that is greater than, less than, or equal to the magnitude of the field at the origin in part B? And justify your answer. And then it gives us the distance between each charge and the origin and asks us to find the electric field in each case. Well, again, at first glance, this looks like this is going to be a lot of calculation work, because scenario A has 3 charges, scenario B has 4 charges. If I have to find the electric field, the process would be find the electric field contribution from each individual charge at that location, then add them all up to find the answer. But there isn't, like I said, much less work involved than this. So here I just blew up the picture a little bit for illustration purposes. What does the electric field look like from each of these charges? Well, I draw electric field as a vector, and an electric field is at a location. And one of the hardest things, at least was for me, for many people about electric fields, is that electric fields exist in locations where there are no physical objects. So the center of these charge scenarios is a place that is empty of any sort of object, but we can still characterize that location by how much electric field there is there. So the electric field is proportional to the charge of each point charge. We've shown that before, kq over r squared. For example, I could say the electric field at the center in A from my 2 microcoulomb charge points to the right and is a certain size. If it's the first vector I'm drawing, I can draw it any size that I want to. The 5 microcoulomb charge, though, is negative. So the electric field at the center of that crosshairs is going to point towards the 5 microcoulomb charge, and it's going to be larger. It's going to be 2.5 times the size of the 2 microcoulomb electric field contribution, because again, that electric field is proportional to the charge, and all of these charges are the same distance from the center. So then I also have a contribution from the -3 microcoulomb charge that points to the right. And what if I do this same kind of analysis over on scenario B? Well, from the 4 microcoulomb charge, I would have an electric field that is proportional to 4 that points to the right. I would have another contribution that's proportional to 1 that points down away from the +1 microcoulomb charge. I have a third that is to the right that points toward the -1 microcoulomb charge. And a fourth contribution here that points up that is proportional to a 6 microcoulomb charge. Well, if you look at scenario A, the total electric field pointing up is proportional to a 5 microcoulomb charge. The total electric field pointing to the right is also proportional to 5 microcoulombs worth of charge. Individually, it's 2 and 3. In scenario B, I now have overall an electric field proportional to 5 up, right? I have one that's 6 up and then one that's proportional to 1 down. And likewise, I have electric field vectors that total an electric field that's proportional to 5 microcoulombs of charge to the right here. One's proportional to 4, one's proportional to 1. What does that mean? It means actually that both of these scenarios have the exact same size electric field at the center, which again greatly simplifies the calculations, because if we calculate for one, it will be for the other. And in fact, we can do even, well, we only really have to calculate one thing here, I guess you could argue. And that is, I got an electric field in the x direction, I got an electric field in the y direction. I'm trying to find the net electric field. Well, I'm using the electric field for a point charge formula. The electric field in the x direction in scenario 1, but it's going to be identical in scenario 2, is 8.99 times 10 to the 9th Newton meter squared per coulomb squared, multiplied by 5 microcoulombs, that's 5 times 10 to the negative 6 coulombs. Divide that by the 6.1 centimeter distance. I need that to be in meters if I want all the units to work out here. 6.1 times 10 to the negative 2 meters, that's squared, and I find 1.2 times 10 to the 7th newtons per coulomb. So that's the x component of the electric field, but the y component of the electric field is also proportional to a total of 5 microcoulombs of charge. So that means it is also 1.2 times 10 to the 7th newtons per coulomb. And I can find the net electric field by using Pythagorean's theorem, 1.2 times 10 to the 7th squared plus 1.2 times 10 to the 7th squared. Take the square root of all that. I find 1.7 times 10 to the 7th newtons per coulomb, which means that the net electric field in this case is indeed 1.7 times 10 to the 7th newtons per coulomb, 45 degrees above the x-axis.